Okay, welcome to today's tutorial. In this video, we're going to look at force damped oscillation. Force damped oscillation. So, force damped oscillation occurs when an oscillating system experiences both damping and an external driving force. It is when an oscillating system experiences both damping and an external driving force. So, there are two things here. The system is experiencing both damping, which represents the damped oscillation, and an external driving force, which is the force damped what? Oscillation. So this is an equation for force damped oscillation, right? We have mx plus bx plus ks is equal to a or cos open bracket wt bracket close, right? Where your m in this equation is your mass, b is the damping constant, k is the spring constant, your x here is the displacement, your AO is the amplitude of the external driving force, and then this W is the angular frequency of the driving force. And of course, T here is your time, right? So this is just the equation for force damped oscillation. Again, like I said, force damped oscillation occurs when an oscillating system experiences both damping and an external driving force. And this is the general equation for it, like mx plus bx plus kx is equal to AO cos wt, where your mx in this equation represents your inertial resistance to motion or your mass resistance to motion. Bx is the damping force opposing the motion. Ks is the restoring force or the spring force, and then A cos Wt is the periodic driving force trying to keep the system moving. So know what each and all these mean, right? Your Mx, your Bx, your Ks, and your AO cos Wt. Your AO cos Wt represents the periodic driving force trying to keep the system moving, right? Ms is the mass resistance to motion, Bx is the damping force opposing the motion, while Ks is the spring force. So having known that, let's look at natural and resonance frequency. So natural frequency, which is given as WO, is the frequency at which a system oscillates on its own when it is disturbed without an external driving force. Right? So it is that frequency in which a system oscillates on its own when it is disturbed without an external driving force. So the catch here is that there is no external driving force. So the natural frequency depends on the mass and the spring constant. So natural frequency, which is W by formula, is equal to the square root of K over M, right? Where your K is your spring constant and your M is the mass. Right? So these are the two factors that determine the natural frequency of what a vibrating string, right? Then we have the resonance frequency. Resonance frequency, which is given as WR, is the frequency at which the steady state amplitude becomes maximum when the system is driven by an external driving force. So that frequency at which the amplitude becomes maximum when the system is driven by an external driving force is referred to as what? The resonance frequency, right? So unlike the natural frequency, it depends on damping. And by formula, the resonance frequency, which is WR, is equal to the square root of WO squared, which is the natural frequency, minus B squared all over 2M squared, where your B is the damping force constant and your M is the mass, right? So note the difference between the natural frequency and the resonance frequency. Natural frequency is the frequency at which a system oscillates on its own when it is disturbed without an external driving force. So here there is no external driving force. Here, resonance frequency is the frequency at which the amplitude becomes maximum when the system is driven by what? An external driving force, right? So note the difference between the two and their formulas. So to take us further, let's look at the first example that we have here. And this question is the equation of motion of a particle of mass 2 kg is given by 2s second derivative plus 4x first derivative plus 7x is equal to 6 sine pi RT. Determine the resonance frequency. And we're given these options. So the first thing I would want to do is to write out the equation that was given to us. So the equation that was given in this question is 2x second derivative plus 4x first derivative plus 7x is equal to 6 sine pi r what t, right? And the equation for force damped oscillation is given as mx second derivative plus bx first derivative plus kx is equal to AO cos WT, right? So this is the equation for force damped oscillation. And we are asked to look for the resonance frequency, right? Determine the resonance frequency. So the formula for resonance frequency WR is equal to the square root of WO squared, which is the natural frequency, minus B squared over what? 2m squared. So this is the equation for calculating resonance frequency, right? Our WO, which is the natural frequency, WO, is given as what? The square root of k over what? M. And what is our k? Our k in this equation is 7. We just compare the two equations, right? This is 7s, this is ks. So that tells us that k is equal to what? 7. So this will be equal to 7, the square root of 7 over m, which is the mass, is equal to what? 2 over 2 is equal to, so 7 divided by 2, that will give us the square root of what? 3.5. 7 divided by 2 will give us 3.5, right? So the square root of 3.5 is equal to 1.87. So our natural frequency WO is equal to 1.87 rad per second, right? This is our natural frequency. The next thing that we're going to do is to look for the resonance frequency. So we have it by formula that the resonance frequency, which is WR, is equal to what? The square root of WO squared minus B squared over what? 2M squared. This is the formula, right? So my WR will be equal to the square root. Our WO, which is the natural frequency, we've calculated it to be 1.87. So that will be 1.87 squared, right? Minus, what is my B? My B is my damping force constant, right? My B here is equivalent to 4. So that will be 4 squared over 2. What is my M? My M is my mass, right? And it is equivalent to what? 2 in this equation. So that will be times 2 what? Squared. So this will be equal to 1.87 squared will give me 3.4969, right? Minus 4 squared will give me, so this is square root, right? 4 squared will give me 16, right? 4 times 4 is 16 over 2 squared will give me, 2 squared is 2 times 2, right? So 2 squared will give me 4. 4 times 2 will give me what? 8. So that will be 16 divided by what? 8. So 16 divided by 8 is 2, right? So that will be the square root of 3.4969 minus what? Minus 2. So 3.4969 minus 2 will give me, so this will be equal to the square root of 1.4969, right? 3.4969 minus 2 will give us 1.4969. So the square root of this number will be equal to 1.2235 rad per seconds. So this is my natural frequency, right? So, and this is approximately 1.22 rad per what? Per second. So my answer here is option A. Very simple and straightforward. So when you encounter a question like this, the first thing that you would want to do is to write out the equation and then write out the equation for force damped oscillation. And also you should remember this formula that your resonance frequency is equal to the square root of WO minus B squared over 2M, where your WO is equal to the square root of K over M, and your WO is your natural frequency, right? So let's look at the next question that we have here. So the question that we have here is the equation of a point mass is 3x second derivative plus 5x 5 derivative plus 12x is equal to 5 cos pi rot plus this phase angle, or plus theta rather. Find the value of arrow. The arrow here is your frequency, right? So find the value of arrow at maximum displacement of the particle, right? So like we did in the previous question, the first thing that I would want to do is to write out the equation, right? So the equation that was given to us is 3x second derivative plus 5x first derivative plus 12x is equal to 5 cos pi rot plus this phase angle, right? And the equation for force damped oscillation is given as ms second derivative plus bx first derivative plus kx is equal to AO cos what? Open bracket WT bracket close. This is my equation for force damped oscillation. Then the next thing I would want to do is to write out the formula for resonance frequency. So my resonance frequency, which is WR, is equal to the square root of W squared minus what? B squared over 2M squared, right? This is my formula for resonance frequency. And my WO, which is my natural frequency, is equal to the square root of K over what? Over M. So if I look at this equation, here is my K, right? So my K is equivalent to what? 12. 12 Ks is equal to what? 12S. I will just compare the two equations and equate them to each other, right? So my K is 12. So that will be the square root of 12 over what is my M? My M is what? Is 3. So over 3. So this will be the square root of 12 all over 3. 12 divided by 3 will give me 4, right? So the square root of 4 is equal to what? 2. So my natural frequency WO is equal to 2 rad per second. But what I'm asked to look for is the resonance frequency, right? So here I'm going to look for the resonance what? The resonance frequency. So the resonance frequency is given as WR is equal to the square root of W squared minus B squared over what? 2M squared. So my WR will be equal to the square root of my W is, we've calculated it to be what? To be 2 rad per second. So that will be 2 squared minus, what is my B? So my B in this equation is what? 5 when I compare. So that will be 5 squared minus divided by 2. What is my mass? My mass is 3, right? When I compare them. So that will be times 3 squared, right? So this will be equal to the square root of 2 squared is what? 2 times 2, right? And 2 times 2 will give us 4 minus, here we have 5 squared. 5 times 5 will give us 25. So that will be 25 over, this is 3 times 3, right? 3 squared is 3 times 3. 3 times 3 is 9. 9 times 2 is what? 18. So that will be divided by 18. So this will be equal to the square root of 4 minus 25 divided by 18 would give us what? 1.3889, right? So 4 minus 1.3889 would be equal to 4 minus 1.3889 would give us 2.6111, right? So the square root of this number, square root of 2.6111 would be equal to 1.6159, right? So our resonance frequency, which is WR, is equal to what? 1.6159, right? Rad per watt seconds. So this is our resonance frequency. But what we're asked to look for in this question is not actually the resonance frequency per se, but the value of R here, right? So what we're going to do is to compare this and this together, right? This and this together, because they are the equation. The first equation that I have here is 5 cos pi ROT plus the first angle, right? Here I have AO cos WT. So if you look at these two equations, they are the same, right? So I can say by comparing these two equations that my WT is equal to what? Pi ROT, right? Or in other words, my pi ROT is equal to what? WT when I compare both equations, right? So my pi is what? What is the value of my pi? My pi is 22 over 7, which will give me 3.142, right? So 3.142 times R times T is equal to, my W here is my resonance frequency, which I've calculated to be what? 1.6159, right? Times T. So my T will cancel out T, right? So my R will be equal to 1.6159 divided by what? 3.142. So what I did here was just to make R the subject of the formula, right? By dividing both sides of the equation by the coefficient of R, which is what? Which is 3.142. So 1.6159 divided by 3.142 would give us 0.514 Hz, right? So this is our frequency. This is the value of R in this question, right?